All right. Well, good morning, everyone. Thank you for your, yep, we're gonna get some feedback there. Thank you for your patience as we've been running a little bit behind this morning. And thank you for finding the right room despite the conflict between what was listed on the website and what was printed in the book. So happy to have you all here. As you know, this is the first, or maybe you don't know, but this is the first topology, algebra, and geometry and pattern recognition with applications workshop. This is a series. Tag DS encapsulates a series of workshops we've been organizing at ICML, related workshops at NeurIPS, and others. And so this is our first one at CVPR, that we have also done one at ICCV. So thank you for being here as we kick this off. We just wanted to kind of share a couple of details. This is our organizing team. 4 of them are not able to be here in person today. So the 2 of us, if you have any questions, if you are a speaker, we will be here, a resource and a point of contact in general. If you have any questions about Tag DS or would like to be involved. We have 2 fantastic keynotes today. Our first one, Nina, will be getting us kicked off here at 9, and our other Vitaly is in the back there. He will be giving us our post-lunch keynote. So please be sure to stick around and come back after lunch. The schedule is up on our website. It is also, I believe, on the CVPR website. So we will be staying to this. If there are people who are unable to join or things like that, we will skip a talk and resume so that people can come, and we will stick clearly to this version of the schedule. Just a couple of logistics. We opted to have all talks live, so they are not pre-recorded. So some of them will be virtual, some of them will be on site. They are going to be recorded from Zoom, and so we will be able to make them available after the event as well. If you are in the room or on Teams, we will be indicating when you have about 5 minutes for the spotlight talks. We will then more assertively in the room, that means I will stand up to let you know you have 2 minutes left, and we will figure out which way we're going to do that on Zoom, but we will be sticking to that schedule again. All of the breaks, you may notice, coincide with the overall CVPR breaks, so they are a bit longer. I believe our first break is at 10 a.m. After Nina's talk, and will be for 45 minutes. So then please resume in this room for the rest of the day. We will also be updating Twitter throughout the day with photos and things like that. So please feel free, if you are enjoying things or have comments, to tag us at taginds. And then just the very last couple things, some upcoming events. We have a workshop coming up at ICML this year. There was a proposed workshop led by Nina and some of her fantastic colleagues that will be hopefully happening again this year at NeurIPS. There's also a AMS mathematical research community next summer that has a lot of tag flavor to it. So if you have students or you yourself are interested in it, please let us know. And then we are, of course, also hoping for additional workshops next year. And so then the final thing before I switch it over to our first keynote is just some acknowledgements that these events really only take place when there is an active community engagement. And so all of the people who submitted to the workshop, as well as participated in the review process and are here in this room, thank you for bringing your energy and efforts to this particular community. So with that, I will stop sharing and I will move this over to you. Thank you. Stop share and mute. I'm unmuted. So we can watch too. Would you like the formal version of the? Whichever you prefer. Happy to provide all of the honor. You can butcher my last name. You can do everything you want. What's that? You can butcher my last name. It's Miaoling, right? Yeah.
Yeah. Sorry, that was the total American way of saying
Yeah, that's it. Miaoling.
Yeah, that lane is long.
I knew I was completely wrong.
It doesn't matter. It's me. Oh, come over to the mic over here. So we will get started with our first keynote of the day. This is Dr. Nina Miaoling. She is at UC Santa Barbara, has a very extensive experience having worked in startup in Silicon Valley, as well as in academia. We are lucky to get to organize future events with her as well. So with that, I will let her take it away with a survey of topological neural networks. Thank you, Tegan. Thank you very much for the introduction. And also I'd like to thank the organizers for putting together this fantastic workshop and all of you for being here today. I'm delighted to be here today. I'm gonna talk about a survey of topological neural networks. So I'm gonna give an overview of this recent yet very fast growing and very exciting field of topological deep learning and show you how it extends geometric deep learning and how it is different from another topology-related field called topological data analysis. So the goal of this presentation will be to give you the keys to understand what are topological neural network and to summarize the literature on topological neural network in this table here, where each topological neural network is represented by what we call a tensor diagram. And as such, we will be able to see what are the current trends in that field, what are the challenges that the community is already facing, and maybe most importantly, what are the most exciting research directions that we should tackle. This presentation is based on two preprints. The first one is titled Architectures of Topological Deep Learning, a survey of topological neural network. And it is a joint work with Mathilde Papillon, Sophia Sandborn, Mustafa Aziz, and myself. And I'd like to highlight the first author, Mathilde Papillon, who has done an extremely good job at summarizing this mathematics-heavy literature, and who also has put together most of the slides that you're going to see today. The second preprint that this talk is based on is titled Topological Deep Learning, Going Beyond Graph Data. This is a longer preprint of 90 pages that gives you everything you need to know in terms of the mathematics that support this growing field. And this is a collaboration with much more people in a team that we call the PYT team. All right, so the outline for the talk today, whose goal is again to give a survey of topological neural networks. The outline is like this. First, I'm going to give a gentle introduction to topological neural networks and explain what they can do for you, what kind of data they can analyze, what type of knowledge they can extract from this data. Then I will present a graphical framework, so pictograms, that we can use to break down any topological neural networks into its essential components, so that you have the keys to understand what these topological networks are, and that you can compare existing topological neural networks that exist in the literature. And in the third part, we'll use this graphical framework to do a graphical survey of the literature. So in that figure, we can summarize every topological neural networks using our pictogram. And what is going to allow us is that we'll be able to see what are the trends, the challenges, and the opportunities for future research in that, again, emerging, but very fast growing field. All right, starting with a gentle introduction to topological neural networks. So at a high level, topological neural networks can extract knowledge from data by exploiting relations between the components of a system. So what are these systems? A first example of system could be a social network, here represented as a graph. The components of this system are the people that are also the nodes of that graph. And the relations between the components are the social relations between these people, here represented as edges of that graph. So a system can be a social network with social relations. But a system can also be a drug interaction network, where each component here is a drug or a protein, if you wish, represented as a node of here a graph. And the relations between the components are now chemical relations between the drugs, and these chemical relations are represented as edges in that graph. So a system can be an interaction network where the relations are chemical relations, or the existence of a chemical relation. And the last example, going to the physical or biophysical world, a system can be a molecule, a protein, here again represented as a graph, where the components of that system are the atoms that made these proteins, here represented as the nodes of this graph. And the relations are the electrostatic relations between these atoms that form covalent bonds, here represented as the edges of this graph. So a system can encode biophysical relationships between these components. Okay, so we said that topological neural networks allow us to extract knowledge from this type of data. So what kind of knowledge can we extract from systems where components have relationships? Well, topological neural networks can allow to answer questions such as, will Alice engage with this content? So assuming that Alice is one of the node of this social network graph, I can answer this question through a classification task. And importantly, this is a node-wise classification because Alice is a node in that network here represented as a graph. In the context of the drug interaction network, topological neural networks can answer questions such as, does this drug interact with this other drug? And again, this can be phrased as a classification problem, but here the classification is edge-wise. I'm considering two drugs and the chemical relation that exists in between these two drugs, and I wish to classify that relation or that edge. And lastly, in the context of the electrostatic relations between the atoms of a molecule, we can answer questions such as, will this molecule bind with this ligand? And so now it's again a binary classification problem. Yes, no, no. But now it's at the level of the whole system, of the whole graph. The whole graph to the whole molecule will be associated a binary label that is either yes or no. Now, interestingly, these three questions can also be tackled by what we call graph neural networks. And as a matter of fact, these three systems are only graphs right now. They are made of nodes and edges. So what do topological neural networks bring to the discussion? Well, we will see that topological neural networks can extend graph neural networks by leveraging non-binary relations to give better answers, we'll define better, and to answer more questions about these systems. So they leverage these non-binary relations or non-pairwise relations. That means that, for example, in the social network system, we may want to incorporate more knowledge about our data set. Maybe we have information about these 3 people sharing something. Maybe this social network is a network of academic researchers, and the relationship denotes which papers they have authored together. So maybe there is a paper that these 3 people have co-authored together, and we want to add that information to our system in order to give a more precise answer to the machine learning question. So this is to give better answers than graph neural networks to the same question. But topological neural network also allow us to answer more questions. So in the center example here, which is the drug interaction network, we may want to answer the question, what is the interaction that is created by taking these 4 drugs together? Because maybe taking only drug A and B together is not going to have any side effect for your body, but maybe taking these 4 together is going to generate a unique set of chemical relations and have adverse effect to you. So that is the polypharmacy side effect problem. And lastly, in the third example, we may want to incorporate the fact that these 6 atoms are not only linked by pairwise covalent bonds, but they also form what we call a benzene ring, which is denoted by this dashed line here. And this means that this benzene ring has additional electrostatical properties in addition to the covalent bonds that form each pairwise relations. So topological neural networks can extend graph neural networks by leveraging these non-binary, non-pairwise relations to either give better answers to the questions that we can ask to graph neural networks, or to answer more questions such that tackling the polypharmacy problem. In what follows, I'm gonna use the following diagrams. So binary relations are gonna be represented with a graph. So the nodes in blue of that graph are the components of the system, and the binary or pairwise relations are going to be represented by the edges between the blue nodes. And by contrast, in topological deep learning, I'm going to use the pictogram that is on the left to denote non-binary relations. So you can see that on the left, we still have these 6 nodes, but now they are linked with more than just edges. We have a relation in pink that includes 3 nodes, for example. And not only that, these relations have different colors. So we have a relation in light pink that includes 2 nodes, but also a relation in dark pink that includes 2 nodes. So we're going to be able to incorporate more information in terms of the relations between the components of our system, not only moving away from non-pairwise relation, but also introducing a notion of ranks between the relations between the components of the system. Okay, so let's go a bit more into the details and explain what we mean when we say that topological neural networks extend graph neural networks. And first, what are graph neural networks? This is a diagram that represents a graph neural network at the bottom here. As usual neural networks, it is constituted of several layers. Here, 2 layers, plus the initial layer that is nothing else than the data set. So in a graph neural network, we start with our data, our relational data that is here. The relational data is the system made out of components, which are the nodes, and the pairwise relations between these nodes. We also have features associated to the nodes and sometimes also to the edges of the system. And we would like to send that data through the graph neural network to answer a question or make a prediction. For example, if the graph, that is the data, represents a molecule, and the features represent something related to the atoms of that molecule, maybe their mass or something, the prediction could help answer the question, to which ligand does this molecule given at input bind? And the way we answer that question is by
updating the features of the graph through the different layers of the graph neural network. So in the input, the features are just the data. But in the next layer, while the graph here is unchanged, the graph is still the molecule, the features that are associated to the nodes and the edges have changed. So you can see we have different colors here than the colors that were given as input. So through the layers of the graph neural network, we're going to update these features until we reach the last layer of the neural network where we pull together the updated features to make a prediction, here to answer a three-class classification problem. Okay, so now how are the features updated? This is what is represented with this dashed gray line that represents what we call message passing. So the way the features are updated is called message passing because it has a nice interpretation in terms of propagation of information. And more particularly, if we look at this node here in blue that has a new feature here, we can think of that feature being the result of messages that have been sent to this blue node by other nodes. So there is an information propagation interpretation, and we'll go more into the detail. Now, topological neural networks extend graph neural networks, and they are built in the same way, except that now, instead of having the graph that was supporting our data, the features, now we have a more complicated structure, we'll call that a domain, which has non-pairwise relationships, and these relationships are also ranked, supports the features, but the rest is the same. Features are updated from layer to layer through a mechanism that's called message passing. And at the last layer, we make a prediction to answer here the same question, the question that was asked to the graph neural network. Importantly, in the message passing scheme, so this dashed line, you have the weights, the learnable weights. So in the context of a supervised learning classification problem, you will put different molecules through this graph neural network and update the weights of each layer until you reach a good prediction accuracy. All right. Now, why do we need a literature review of topological neural network? We need it because there have been two confusions about what topological neural networks and topological deep learning is. The first confusion is the following. It's a confusion between a related field, which is called topological data analysis, which, at least for the wordings I'm using today, is very different from topological deep learning. So you might have heard about topological data analysis. It's a field that emerged about a century ago, and that has been more recently applied to machine learning and even deep learning, for example, in the two papers cited here. So topological data analysis uses different tools. The most known one is called persistent homology. And the goal of TDA is to extract topological features from the data. So maybe I have a data set that is a point cloud, and I wish to know if this point cloud forms a torus, forms a sphere, basically what is the shape of the data. And then I can incorporate this topological or geometric feature into a classical machine learning algorithm, into logistic regression. I can even incorporate these topological features that I just extracted with TDA into a neural network. For example, with this paper, topological graph neural network. But this is different with what I'm going to call topological deep learning here. Because topological deep learning already knows the topological features of the data set. It is not about extracting them. I already know the topological features, which are the relations between the components of my system. And I want to exploit these known topological features to have more expressive neural networks. Questions?
Silly question, but who was it in 1927? Surely it wasn't Herbert Evans, not that old.
Okay, I'll check. Thanks for the comment. All right, and the second mass confusion, which is the reason why we need this literature review, is what I call notation chaos. So across the works that have been published since for a few years ago, you can find these type of equations. It's because the field has been driven by mathematicians. And so what is in these papers is often mathematical heavy. And more than that, different authors are going to use different notations, because maybe a slightly different notation is more suited to their current application. Actually, the notations that you see on the screen all represent the same thing. Yet it's difficult, at least to me, to see that they are representing the same concept. And so this notation chaos makes it difficult for practitioners to enter this field. So I'm working with biomedical data. I know that there are relations between the components of my system, but I have no idea how I can use the research from that field. And not only it's a problem for practitioners, I would say it's also a problem for the mathematicians working in that field, because it is hard to compare a new model with the past model without having to go through the trouble of rewriting all the equations. And by the way, as a result of this literature review, I'll mention it in the end, we have rewritten all the equations of the papers of topological deep learning. It's available online on the GitHub repository. Okay, so that was the introduction to topological neural networks at a high level. These topological neural networks are neural networks that extend graph neural networks from geometric deep learning and allow to compute with relational data. Now I'm going to introduce a graphical framework to give you the keys to understand any topological neural network, and more particularly to break a topological neural network down into essential components. And to each of its essential components, we're going to associate a pictogram so that we can give a graphical survey of the literature review. Stating the goal in English, our goal is to provide an intuitive graphical framework that is going to elucidate the topological domains, so the different kinds of relations that we can incorporate in the data, and the deep learning mechanisms that are used to do this message passing operation that we see in the literature. We're going to break this framework into three parts. One, the topological domain, which is this thing, which is the domain that supports the features. So the domain, a social network, a molecule. Two, the neighboring structures. So this is not necessarily illustrated here. Neighboring structures represent a choice that is made by the researcher in terms of how features can be updated from one layer to the next, in terms of, more particularly, which nodes can send information to which other nodes, or which edges can send information to which other edges or faces, etc. And third, message passing. So we'll explain what these gray dotted lines are. Starting with the topological domains. So the domains of topological deep learning on the right generalize traditional discrete domains on the left, in that they can allow you to incorporate more precise information regarding the relations between the components of your system. So relations, for example, social relations between people in a social network. In the traditional discrete domains, we have a set of data points with no relations model whatsoever. And we also have the graph, which model pairwise relations between pairs of components of the system. Have Alice and Bob co-authored a paper together. Now, the domains of topological deep learning generalize the discrete domains by being more flexible in the way we can incorporate relations between the components of a system. And we can do that in two ways. First, adding part-whole relations, and second, adding set-type relations. In the part-whole relations, we find the simplicial and the cellular complexes. Now, these domains add notion of faces. So for example, triangular faces, or volumes, for example, tetrahedrons. And they represent part-whole relations because they have this constraint that any face needs to be bounded by edges. Any volume needs to be bounded by faces, etc. So in some sense, the face contains the edges, the volume contains the faces. Now, the simplicial complex has rigid geometric constraints, which are that the faces have to be triangles, the volumes have to be tetrahedrons, etc., which is a rigidity that is relaxed by the cellular complex, where faces can be squares. They don't have to be triangles, or volumes don't have to be tetrahedrons, etc. That's for the part-whole relations. Now, in terms of the set types relations, we have the hypergraph. Now, you know that in contrast to the simplicial and the cellular complexes, the hypergraph does not have notions of faces and volumes. We're still working with only nodes in blue and edges in pink. But it generalizes the pairwise relation of the graphs in that edges in pink can now have more than 2 nodes. So for example, here we see an edge that has 3 nodes, and that is therefore called a hyperedge. But there is no notion of part-whole relations. It's just that the edges can be larger and denote subset of the data. So for example, these 3 others have co-authored the paper together, which doesn't necessarily mean that these 2 authors have co-authored a paper with only them 2 as authors, or that these 2 have a paper with only them 2 as authors. All right, so this is a bit abstract, so let's see how these domains can be used to represent relations in actual data sets. And let's start with the simplicial and the cellular complexes. Now, these 2 domains are very powerful in representing geometric data. For example, the molecule shown here. Using the simplicial complex, you can add triangle. So you can add the information that you have cyclopropane triangles in your molecule. And with the cellular complex, you can also add non-triangular faces. And so it allows you to add the benzene rings that are here. These 2 domains also are very powerful in representing meshes. So another type of geometric structure, which is what's shown here with the 2 meshes. The difference between the simplicial and the cellular is that in the simplicial case, faces have to be triangles, whereas in the cellular case, you can have faces that are pentagons, octagons, or things like that. Now, moving to the hypergraph case, here we have an interaction network of proteins. And thanks to the hypergraph, we can model the fact that proteins A, B, G, and F are interacting together. If you have these 4 proteins, you're going to have a chemical reaction. And this is not a part-whole relation because these 4 proteins interacting together doesn't mean that if you put only protein A and protein G together, you're going to have a relationship or a chemical interaction. And lastly, in the center, we have the more general domain, the more flexible domain, which is the combinatorial complex domain that incorporates ideas of both the part-whole relationships and the set type relationship. So it can extend the cellular complex in the way the cellular complex was representing this protein, because not only we have the geometric structure that we get from the cellular complex domain, we can also add the functional structure of this molecule. So we can add the fact that these 6 atoms form an amino acid, or that the 3 atoms form a carbocyclic acid. So not only we have the geometric aspect of this molecule, we get the functional aspect of this molecule. And the combinatorial complex also extend the set type relationships of the hypergraphs because it can represent the protein interaction networks by adding more knowledge to it. So now you see that the sets that represent the chemical interactions between the protein have colors. We have pink for a low interaction and maybe red for more powerful interactions. Yes.
So I'm trying to understand the sort of context.
Mm-hmm.
Is it basically a more richly tagged hypergraph?
More rigidly.
Is it a more richly tagged? Is it a hypergraph where some of the hacker edges can extra information attached?
Yes, you can see that way, and that extra information will be a notion of rank. So here represented with only two ranks, a light pink and a darker pink, but you have a notion of ranking between the relations in the hypergraph. You can also see it as a generalization of the cellular complex, where you do not have the requirement that a lower ranked cell is included in a higher ranked cell. So for example, this edge here is not included in that phase, is not included in that phase. So you break down the partial relationship.
So the difference to cellular complex is that you don't force the existence of lower dimensional cells?
Yes, yes.
Because I don't see how that's two edge in the vertical complex wouldn't be represented in the cellular complex.
Because in the cellular complex, as in the regular cellular complex, any phase needs to be bounded by edges, which means that the edges, which are in lighter pink, have to be included in the phase. Now, if you move to irregular cellular complex, which is something you might be more familiar with, then you'll be able to have more exotic structures.
Thank you.
Great questions, thank you. And so how do we choose between all of these topological domains? Where in order to choose the topological domains, it could be interesting to go back to the questions that we want to ask to our relational data. So for the three domains on the left, it could be, what are the properties of this molecule? And if you believe that adding the functional groups or more information about the relationship between the atoms of this molecule can help answer the question, it seems intuitive that you would want to use a more flexible domain that allows you to incorporate this information that you believe will help answer your question. And similarly, for the case of the hypergraph here, if we want to know if two drugs interact together, or maybe four drugs interact together, then we may want to have something that is more general than a graph. That being said, it comes at a cost. So it's great to use this more flexible domain to incorporate more information in terms of the relational data. However, you might be paying this in terms of complexity. So you're adding more structures, and so therefore the message passing scheme that we're going to see is going to be more costly. So you need to ask yourself the question, do you believe that this additional relational structure will help answer the question? Okay, moving on to the second part of the framework, which are the neighboring structure. And this notion of neighborhood is really what gives the name to topological deep learning. So what is the neighborhood of a cell? Here, I use the word cell to refer to either a node, an edge, or a phase, a volume. The neighborhood of a cell is loosely defined as cells, all the nodes, edges, faces, and volumes that are close to that cell in some sense. And the fact that they are close to that cell will mean that they can pass messages to that cell within the message passing scheme that is used through the layers of a topological neural network. Now, I've put quotes in all of this because this notion of neighborhood and closeness is basically up to the researcher. So the neighboring structure will be chosen by the researcher who is designing its topological neural network. For example, the researcher might choose that the neighbors of this face, this benzene ring, are these three other faces, the two triangles and the other benzene ring. Or the researcher might choose that the neighbors of this node here, which is an atom, are the three covalent bonds that are next to it. Or the researcher might choose that both are true and that we have different types of neighborhoods for this one molecule. Okay, so there is a choice that needs to be made by the practitioner or the researcher designing a topological neural networks. What are the different options? So a cell Y, and again, the cell is either a node in blue, an edge in green, or a face in dark pink, has, roughly speaking, 4 possible neighborhoods. There are more. I mean, you can define whatever you want to be a neighborhood, but there are 4 common traces. The first one is the neighboring structure of the boundary. The boundary is defined, so the boundary of a cell Y is defined as the cells of ranks -1 that are connected to it. So for example, if we consider this edge Y in pink, the boundary of this edge are the two nodes that are connected to it, which are the two nodes here in blue denoted by X. And likewise, the boundary of this space Y are the three edges that are one rank lower and connected to it. So at a high level, the boundary structure will allow us to send messages in the message passing scheme in between layers of the neural network between cells of rank R to cells of rank R -1, from edges to nodes, or from faces to edges, etc. And the way it's going to be done is through the use of a matrix called the boundary matrix, one example of which you can see here. It's basically a matrix of 0 and 1s, sometimes -1s if you have orientations within the CVPR complex. But basically, it is expressing the fact that A is in the boundary of the edge AB, but is not in the boundary of the edge of the face BCD. This is a boundary matrix, 0 and 1s. The second neighboring structure is the co-boundary neighboring structure, and it's viewed in terms of matrix, nothing else than the transpose of the boundary matrix. And so the co-boundary of a cell Y corresponds to all the cells that have one rank above and that have Y as their boundary. So for example, the co-boundary of this node Y is all the edges, one rank higher, that are connected to it and that have Y as their boundary. And likewise, the co-boundary of this edge Y is all the faces X that are connected to that edge Y and that have that edge Y as their boundary. And we're gonna, in the message passing scheme, we're gonna use the transpose of the boundary matrix, which is gonna give us a matrix of 0 and 1s again. The third neighborhood structure is the neighboring structure of lower adjacency. So lower adjacency is defined as all the cells that share a boundary delta with Y. So for example, the adjacency of this edge Y is all the edges, same rank, that share a boundary, that is a node, with Y. And likewise, the lower adjacency neighborhood of this face Y are all the other faces, same rank, that share a boundary, that is an edge, with that cell Y. So it allows you to send messages from cells of same ranks, so from edges to edges, from faces to faces, through the boundary they share. So for example, Y will be able to send messages to X through the node it shares with it. And we go through a boundary, so we go through a node that is one rank lower. That's why it's called the lower adjacency. And by contrast, we have this notion of upper adjacency, which corresponds to all the cells X that share a co-boundary delta with Y. So we'll be able to send messages from cells of the same rank, but this time by going through the co-boundary, so by going through a cell that is one rank higher. For example, the upper adjacency of this node Y is all these other nodes, same rank, that share a co-boundary, that is an edge, with Y. And that is the more known notion of adjacency that you might know from a graph. This is the adjacency matrix or the adjacency structure of a graph. But we can also have it for the edges. So for example, these two edges are in the upper adjacency neighborhood of Y because they share a co-boundary with it, which is the face here. And so this allows us to send messages from cells of same rank by going through a cell of one rank higher. So we have these 4 neighboring structures that we can choose from, or we can design our own neighboring structure. How do we choose? Well, first of all, it depends where you have features. So if you don't have any features on, let's say, the faces, because you have a graph, then you cannot use the upper adjacency of the edges, because you cannot go through the faces. And then it really depends on which is going to work the best for your problem. And we're going to see that different architecture have made different choices. Going to the third part of the framework, which is finally the message passing. So the message passing is really going to define the topological neural network. And actually, when we're going to describe the topological neural networks of the literature, we're really going to define what is their message passing. So we're going to identify a topological neural network with the mechanism that updates the feature from one layer to the next. To represent that, each layer will have this pictogram associated to it for each of its cells. So I'm going to use one blue dot to represent all the nodes of the domain at one given layer. And a pink dot if I want to represent all the edges of that domain at a given layer. And I'm going to use another dot to represent all the nodes of the domain at the next layer. And I'm going to use some type of arrow to indicate in that case that nodes are sending messages to nodes from the layer T to the layer T+1. So that's going to be one single pictogram that represents how information travels, here only between nodes, from one layer to the next. So let me introduce the pictograms that are going to describe the message passing schemes. So first, the researcher needs to choose which cells will send messages to which cells and via which neighboring structures. So for example, here, one example of message passing scheme could be to decide that only nodes are going to send messages to nodes, and that's it. And the neighboring structure they're going to use is the upper adjacency matrix, so by going to the edges. But we could have other designs. We could design a message passing scheme where edges send information to edges to the lower adjacency. And same thing to send messages between cells of different rank. Second, the researcher needs to choose the type of message passing. And we have 3 choices that are common in the literature. Either a convolutional message passing, or an attentional message passing, or general message passing. And these are 3 choices that are known from graph neural network. For these 3 choices, we're going to use 3 different pictograms. So let's say I have edges that send information to edges from one layer to the next. If the message passing is convolutional, I'm going to use that black arrow. If the message passing is attentional, I'm going to use an orange arrow. And if the message passing is general, I'm going to use an arrow with a larger width. Note that we can have an attentional mechanism even for a message passing that is not convolutional, that is general. I'm going to show you equations of what a convolutional message passing looks like. Here it is. So for example, this pictogram here, what does it mean? It means that at layer T, the edges Y send messages to edges X's that share a boundary with it. And it's a convolutional message passing, which means that the message has this equation. There is a message going from cell X, cell Y to cell X that are both of rank 1 that goes through this neighboring matrix, more or less zeros and ones. I mean, it has some zeros. This is the feature of Y at layer T, and this theta here means the learnable parameters. So to each of these pictograms corresponds some type of equation, the simplest of which being the convolutional type. If you have a more complicated type of message passing, just imagine that this equation is a bit more complicated. All right, so that's define the message. The next choice that the researcher need to make is to how we're gonna incorporate features coming from different cells. So maybe there are many different edges that send information to that one edge X. How do I aggregate this information? If the aggregation is done with a sum, we're gonna use a black arrow. If it's more complicated than the sum, we're gonna use this little banana here. And third, if we have different neighborhoods that send information to the same cell, so for example, X is an edge, is receiving messages from other edges, but also receiving messages from nodes, then we need to know how we're gonna aggregate this information across, so inter-neighborhood. And here, same strategy. If the aggregation function is a sum, we're gonna use just these arrows. And if it's more complicated than the sum, in our literature review, we're gonna use this banana. And lastly, when this cell X gets all of this information with different neighborhoods, each neighborhood having different cells, that cell needs to update its feature, because this is the whole point of the message passing scheme, is for the cell to update its feature at layer T+1. And we're gonna have two pictograms. Either it's only using an update function, for example, a sigmoid, or it's using an update function that takes into account the feature it had at the previous layer. In that case, we'll have a circular arrow. Let's see one example of this graphical framework. So in the literature review, you're gonna see pictograms like this. This is a simplified version of a topological neural network published by Bodnar and co-authors in 2021. So what does it mean? We see, so bottom level is layer T. Up level is layer T+1. And these arrows represent the message passing scheme. So we see that in this neural network, we have nodes that send information to edges. We have edges that send information to edges, and we have faces that send information to faces. For each of this message passing scheme, we have different neighboring structures that are used that specify which nodes can send information to which edges. Here, these are the nodes that are in the co-boundary of the edges. Which edges can send information to the edges, etc. We see that each arrow is just an arrow. So it means that in terms of the aggregation per neighborhood, it's only a sum. And then the aggregation across neighborhood is also only a sum. And these are the sums that you can see here. Red is the message passing, it's convolutional. Orange is the aggregation for each of the 4 neighborhoods, actually. You have 3 equations because I needed space. So the 2 Laplacians are here. Green is the aggregation across neighborhoods. It's a sum. Yeah, indeed, we only see arrows. And blue is the update function. All right, so now that we have our graphical framework, let's use it to review this literature. And let me restate our goal. The goal is to provide or to use this intuitive framework, so this pictograms notion, to elucidate the topological domain and the deep learning mechanisms that exist in the literature on topological neural network. We're going to fill this table together to give a graphical summary of what has been done in topological deep learning. The topological domains are going to be the rows of this figure. So we're going to have neural networks that operate on hypergraphs, on simplicial complex, cellular complex, and combinatorial complex. And the deep learning mechanisms are going to be the columns of this table, where on the left, we have the standard convolutional neural network, and on the right, we have more complicated things, attentional convolutional, or a general message passing scheme. You can think of more complicated equations than the one I had showed you. And we're going to see how these topological neural networks generalize the graph neural networks indeed, because a graph neural network, a graph convolutional neural network, would be represented by this pictogram. Nodes send information to nodes from the layer T to the layer T+1 through the adjacency matrix, so through edges. And you're going to see that the pictograms of this table will be indeed more complicated than the graph convolutional network pictogram. Okay, so let's start with topological neural networks that operate on the hypergraph domain. The hypergraph domain is one of the oldest domains on which topological deep learning has been employed. Before hypergraph neural networks, the strategy to do deep learning on hypergraph was to take the hypergraph, collapse it into a graph, and then use graph neural networks. However, this was losing important structural information. And so the first neural network to really include the hypergraph structure was the one published here in 2020. And you can see that it introduced this idea of having nodes sending information to edges and then back to nodes. So blue, pink, blue, that has been used in hypergraph neural networks afterwards, because you can see that a lot of the other neural networks have employed this strategy as well. I'd like to point out this neural network here, published in 2021, because it is one that deals with the problem of over-smoothing. Over-smoothing is a problem encountered in graph neural networks, and maybe unsurprisingly, it applies to topological neural networks. And in this paper, the authors have employed strategies from graph neural network literature to tackle this problem for the hypergraph neural network. I'd like to point out this one here too. You can recognize the red arrows that denotes attention mechanisms. So this is an example of how successful models from the graph neural network literature have been applied to topological deep learning. Here it's the application of transformers to the hypergraph domain. Moving on to the simplicial domain, so simplicial neural network. First, we have this neural network that looks very much like a graph neural network, because you can see that nodes send information to nodes only. Edges send information to edge only, and faces in dark pink send information to faces only. A model that had been generalized to cells with any dimension. So here we use the color yellow to say any cell can send a message to cells of the same rank in the generalization of graph neural network. It's only a bit later that Bunch introduced this simplicial complex neural network where information is allowed to travel across cells of different ranks. So we can see, for example, the nodes send information to edges, but also to nodes. And we have these crosses that indicate information going across cells of different ranks. Things can get more complicated as we add different levels in these message passing schemes. I'd like to point out this neural network, which uses an attention mechanism, which you can recognize through this red arrow. It's also the only topological neural network that is heterogeneous, in the sense that it can deal with features of different dimensions defined on its node edges and faces. In the cellular domain, we have less topological neural networks, way less. And we can also observe that the architectures that have been proposed here really mimic what has been done in the simplicial case. So we can see that the neural network at the bottom looks very much like the corresponding simplicial neural network just above it. Similar strategy, again, is used for these two neural networks. And even in the attentional case, again, denoted by the red arrow, we can see that the only attentional cellular complex neural network employs a similar strategy as its counterpart from the simplicial complex deep learning world. And lastly, in the combinatorial domain, there is only one paper that has proposed 3 different topological neural networks. And so it's an exciting area of research to determine how much this new domain can bring to the field. In terms of expressiveness, the more flexible the domain, the more expressive it is, in a sense defined by the geometric learning literature. And in terms of performance, what do we get? So in this table, again, the rows represent the domains, and the column represent different machine learning tasks that these domains have been trained on. Node level classification will at least a node of the social network engage with this content. edge level or complex level machine learning task. We can look at the level of benchmarking that has been performed for each of these models. And you can see that almost half of them have been compared to graph neural network. This is what is shown in green. In that context, we see that most of these more flexible domains have been shown to outperform the graph neural networks in terms of prediction accuracy, for example, classification accuracy. However, they are not always compared to the graph neural network in terms of complexity and time it takes to process information. And maybe more importantly, they are not always compared to other topological neural networks. So let's say another is proposing a new hypergraph neural network. Most of the time that hypergraph neural network is benchmarked against a graph neural network, sometimes to another hypergraph neural network, but almost never to, let's say, a cellular complex neural network. So it's difficult to compare across domains. And so what are the open questions in the field? Well, I think we do need more benchmark data sets and interesting benchmark data sets which actually have higher order relationships, not just a graph that I have transformed into a simplicial complex just because I wanted to test my simplicial complex neural network. And also these models would need to always include a measure of complexity, not only show the performance in terms of accuracy, but how long did it really take to train that model? We would like to see more models that address outstanding problems from the graph neural network communities and problems that are known to be forwarded to the topological deep learning community, such as oversmoothing and overquotient. More dynamic topological neural network will be interesting, where dynamic topological neural network means a neural network where the domain can change from one layer to the next. It doesn't have to be one graph from one layer to the next. And lastly, maybe generalizing to irregular complexes, which are illustrated here. We propose to address these questions together. So with the fantastic organizers here, we are organizing a topological deep learning challenge at ICML 2023 in the ICML edition of this workshop, where the goal is to implement topological neural networks that are reviewed in the table I just showed you, so that we have them in one shared code base and we can actually benchmark them. And to make that task easier, we have rewritten all the equations that have led to the graphical literature review that I just showed you using the same notation in a GitHub repository called awesome TNMs to make it easier on the participant of the challenge to actually implement this model. In conclusion, I hope I've given you an introduction to topological neural networks, introduce a graphical framework to help us think about what are the different key components of such neural network. And we've used this graphical framework to survey the literature by completing this table. Thank you very much for your attention.
I have some questions, but let's see if anybody else has them first.
It seems to have representation was from starting to end. So I haven't created hours. Last one time we can see the conditions for the system. The meshes that really is going to have random meshes. So that maybe since these are not much of a group, so as they have very much those that so it's like the right representation of
during the layers. So for example, you start with some, so by representation, you mean the type of domain, for example? What do you mean by representation?
Representation and their relationships.
Yes, yes. So here it's the same across the layers. That's what we call the static topological neural network, but you can have dynamic topological neural network that would change the representation from layer to layer. So you could have something that has a different number of nodes here and other like, and maybe something different here. In that case, we call it dynamic. I remember seeing one paper that does that type of dynamism, and basically from one layer to the next, a clustering mechanism is applied so that you get a coarser and coarser domain or representation as you go through the layers. I think they do it automatically with some notion of k nearest neighbors. And that would be the equivalent of the pooling that you see, like argmax or average pooling that you see in convolutional neural networks on images, where you reduce the size of the image from one layer to the next if you use max or average pooling there. But indeed, I remember seeing one, maybe a few more, but definitely not that many dynamic topological neural networks that are not graph neural networks. Yeah, thank you.
Other questions? So, and then sort of, sorry, Davis.
Yeah, so you mentioned like a couple of times this trade-off between expressiveness and complexity. How do people go about formalizing this trade-off?
Yes. I mean, you can, in terms of the complexity, you can actually just compute the number of elementary operations, which is not and then how do people go about balancing this trade-off? Well, something that saves topological neural networks is a natural problem, which is oversmoothing. So oversmoothing is a problem that is encountered in graph neural network, which is the tendency of the features as they are updated from layers to layers to have no information whatsoever, because all the features of the components of the domain are going to converge to the same thing. And for this reason, so that happens in graph neural networks, that happens even more in topological neural networks because nodes and edges and faces and more components are talking together. And for this reason, very often we have very shallow neural networks. So 2 layers, 3 layers, etc. And so to some extent that saves the day because you only have 3 layers. So the complexity is not that bad. And the hope is that since you can send information faster, so from one node to the other, you don't have to go through all of the edges that connect them. You can go through the faces and it goes faster. The hope is that with less layers, even though the computation of one layer is going to be more expensive, with less layers, you're going to be able to achieve the same goal. In terms of how so that's how they address the complexity problem. In terms of how they evaluate it, I don't remember seeing theorem, but I'll have to double check, but then it's more benchmark needed to actually see what's happened. Great question.
So my question was more just what your thoughts are on some of the biggest roadblocks. We've seen huge movements in generative AI, especially in the last 6 months, and this notion of foundation models. Do you think that something like a topological foundation model could exist, or general philosophical question?
Yeah, that's a great question. So I think topological neural network could be used to build a foundational model. So I could imagine a topological neural network being trained on the academic literature, maybe as a hypergraph neural network, where nodes are academic researchers and edges are when exactly 2 researchers have published a paper, and hyper edges, 3 researchers, for example, when these 3 people have published a paper. The thing is with foundational models, though, is that they need a lot of data, or at least the ones that are very famous have been trained on a lot of data. And so that goes back to the other question, which is this even feasible with something whose computational complexity can be exploding? So what I would think would be to first train a foundational model on a lot of data, but that model will not be topological, and maybe refine it with a topological neural network on less data. And I don't think that has been done. So yeah, that would be exciting.
Well, let's thank the speaker again. Thanks, Nina.
Thank you.
We will be on break until 10:45 for the morning coffee break. I don't know how much they're doing here in the east wing versus in the west wing, so I apologize if you have to go back and forth. If you are speaking in the next window between 10:45 and leading up to lunch, our first 4 spotlight talks, please stick around just for a second so we can go through logistics for getting your slides up if you are in person.
Okay, well, welcome back everyone from the break. We're going to have 4 spotlight talks during this session, and then we'll take a break for lunch. We have our first speaker up here right now, Anki from the Imperial College of London. I'll just switch over the display to you, and then you should be able to go.
All right, work. Okay, cool. Hello, everyone. My name is Anki. I'm a final year PhD student at Imperial College London. And today I'll be presenting our work on topology preserving compositionality for robust medical image segmentation. I'll first give a brief overview of medical image segmentation. So medical image segmentation is quite unique because anatomy is consistent among patients. This means that there's very limited structural and spatial variability in the segmentation maps. However, in medical imaging, we often acquire the images on different scanners across different sites. These different scanners often have different acquisition protocols, which leads to textual shifts from one scanner type to the next. Unfortunately, in deep learning, these deep learning-based segmentation models are not very robust to textual shifts. So if we train on one scanner type and test it on another scanner type, we often get a degradation in the segmentation performance. This is particularly true for CNNs, which show textual bias. So we therefore propose a simple recipe in order to combat this. We basically exploit the limited structural and spatial variability in medical image segmentation, and we propose to constrain the latent space of any deep learning-based segmentation model to a finite number of components to construct a dictionary. We then sample this dictionary in a topological preserving manner in order to construct the segmentation output. And the reason why we do this is because otherwise we'll be sampling this dictionary independently, which will lead to anatomically implausible segmentation outputs. The diagram on the right gives an intuition into how we want our method to work. So if we sample these 2 components from our dictionary and then compose them by summation, we'll get this as an output, but this does not match the label. Whereas if we sample these 2 components and then compose them by summation, we'll get this as the output, and this does match the label. And this provides the motivation of how we're going to approach our work. So how do we preserve topology? So we use a popular area of topological data analysis called persistent homology. So we can use persistent homology to provide us with gross topological features for segmentation maps, such as the number of connected components, holes, and voids. There are 2 key ingredients to persistent homology. The first is the connectivity of your topological space. And in our work, as we're dealing with images, we construct what we call cubical complexes to construct our topological space. The second ingredient of persistent homology is the filtration function. In our work, we use an intensity-based filtration function as we're dealing with images. We use this intensity-based filtration function to construct a number of cubical complexes at different thresholds. Now, this together forms a nested sequences of cubical complex, where one cubical complex is a subset of the next cubical complex, and this is shown here. Now, for each cubical complex, we can calculate the d-dimensional topological features which exists. And then using this, we can calculate when a topological feature is born and dies. This essentially creates a tuple of birth and death times, which we use to fill in something called a persistence diagram. On the right, we have an example. So if you look at the bottom, we have the labels for something called the myocardial segmentation. And what you see here is that there is one connector component, which is born at 1 and dies at 0, highlighted by the red circle, and a hole, which is also born at 1 and dies at 0, highlighted by the blue square. Above, we have the output of a deep learning segmentation model after we apply the softmax function. And this is a continuous output from 0 to 1. Here you also get one connected component and a hole, which is born at 1 and dies at 0. But we also get these topological features along the diagonal, which die instantly, basically, which represents noisy topological features. And this is what you get when you're dealing with continuous outputs, essentially. Here, we give a brief overview of how our method works. So firstly, we want to map our image to a continuous latent space using an encoder. We then collapse this continuous latent space to a finite number of components to construct a dictionary. And the way we do this is using vector quantization. In vector quantization, we divide our continuous latent space to a finite number of vectors. We then minimize the distance between each of the vectors in the continuous latent space with its nearest component in the dictionary. Then we replace each vector in the continuous latent space with its nearest component in the dictionary to create a discretized latent space, known here as Z hat. If you look at the previously, so this is the equation above for vector quantization. And you can see this is quite similar to k-means, except here we're collapsing all the vectors.
Zoom slides.
Sorry. So in this equation for vector quantization, you can see this is quite similar to k-means, except here we're collapsing all the vectors or points around the centroid onto the centroid. And this is what makes discretization different from clustering. Going back to this, what we do next is, once we have our discretized latent space, we want these features to be disentangled, i.e. unique. And we do this by applying a shape disentanglement loss, shown here. And essentially what we do is, we minimize the dot product of all the discretized features in our latent space. What this leads to is it leads to our features only representing shape. Because these discretized features are calculated after a softmax function. So essentially, what you're finding is that if you sum over all of these features, it will equal to 1. And if you do the dot product of all these features, given this loss function, it will equal 0. This therefore means each discrete feature can only be binary, and hence only represent shape, and therefore texture is removed. Going back to this, what we do now is we construct our low-dimensional class segmentation outputs, shown here, by summing over the discretized features. We then want to minimize the topological loss between these low-dimensional class segmentation outputs and the low-dimensional labels. And the way we do this is by this Wasserstein distance loss, which minimizes the Wasserstein distance loss between the persistence diagrams for the low-dimensional class segmentation output and the persistence diagrams for the low-dimensional labels. We also want to apply our method in a hierarchical manner, and we do this by summing over the low-dimensional class segmentation outputs to create low-dimensional foreground segmentation output, shown here. And again, we minimize the topological loss between our low-dimensional foreground segmentation output and our low-dimensional label. We apply our method in a deeply supervised manner at each level of the decoder until we get to the final segmentation outputs. We then carry out a number of experiments to show the benefit of topological preserving compositionality, which we abbreviate to TPC. In our first set of experiments, we evaluate segmentation performance under a number of perturbations in the input space. We applied various perturbations. For example, in the first set of perturbations, we applied noise-based perturbations such as textural changes, such as Gaussian noise, Poisson noise, and salt and pepper noise. We apply spatial perturbations in the form of Gaussian blur and motion artifact. We also apply contrast and intensity-based perturbations. And we incorporate TPC into 3 different types of models: UNet, NN-UNet, and SwinNet UNet R. And what you see in the table on the right, we see that by incorporating TPC, there's far less degradation in the segmentation performance under the various perturbations compared to not incorporating TPC. We can visualize this with an example below, whereby incorporating TPC produces segmentation maps which are much more anatomically meaningful. And you can also see that the number of connected components better matches the label. So essentially, our method is essentially ignoring the perturbations, and it's also kind of acting as a counting loss function, which is useful for when we have a lot of labels in the output space, essentially. We then evaluate our method in the single domain generalization setting. And in this setting, essentially, what we want to do is we train on one domain and test it on a completely different domain. We evaluate our method on two different types of data sets, the cardiac and the prostate MRI data sets, where there's a large acquisition shift, where there's a different scanner type and different acquisition protocols. We also compare our method to different SDG methods. We compare it to two augmentation-based methods, big org and cutout. We also compare to ADV bias, which is an adversarial data augmentation method specific to MRI. We then also compare it to RANDConv, which is basically applies randomized convolutional layers to remove textual information. And we finally compare it to GIGAN, which is a self-supervised method which solves jigsaw puzzles. Our baseline model is a UNet, basically. And you can see here, our method outperforms the majority of the SDG methods and competes favorably with the best one, which was big org. And in the diagram below, you can see our method also, again, produce segmentation maps which are more anatomically meaningful. We then carry out an ablation to evaluate each component of our method. We evaluate this method in the single domain generalization setting. And again, we compare it to cardiac and prostate MRI. We also evaluate on cardiac and prostate MRI data sets. And you can see that by incorporating each component of our method, the dictionary, followed by the class topological loss, followed by the foreground topological loss, the segmentation incrementally improves. And this holds true for both the dice score and the Betti error, and shows that each component of our method is important in order to improve the robustness of segmentation models. In conclusion, we exploit the limited structural and spatial variability in medical image segmentation and propose a method called topological preserving compositionality. We show that our method improves the robustness of various segmentation models under both various perturbations and domain shifts. Thank you for listening.
Thank you. Do we have any questions? So I apologize if I missed it, but when you were talking about using the P-Watt switching distance in there between persistence diagrams, you were operating directly on the persistence diagrams, or have you thought about if you could get increased efficiency by integrating some of the generative type models where people try to synthesize what the persistence diagram would look like or those distances?
No, it's just directly on the class maps.
Did that pose any sort of computational bottlenecks?
It does because one of the advantages here is that these are low dimensional, so they're quite small, but we're applying in a deeply supervised manner. So you're applying it at each level. And then when you go to higher dimensional outputs, it does slow it down by quite a bit. Yeah.
And are you doing is there any necessary like pre-processing on your images on the front side?
Yeah.
To make sure that the pipeline works?
Yeah, so we have to normalize our images between 0 and 1. We're dealing with MRI data, which is very heterogeneous. So everything has to follow a very strict pipeline in order to make this method work, essentially.
Any other questions?
And I'm curious, have you been working with any folks in the medical industry to understand like the different types of errors and how to like, give an optimal result back to them as doctors?
No, not yet. Hopefully, eventually, yeah.
Perfect.
Well, thank you again.
Thanks so
We'll give our
much.
next,
Thank you very much.
our next speaker will be live, but virtual. So we're gonna go get them set up on the computer. We'll do a quick sound check and make sure. Tim, because you'll want to unmute your computer, right?
We are unmuted. If our next speaker would like to share her slides.
It says you cannot start screen share while the other participant is sharing. Okay.
Eugene, can you do a mic check for us?
Yes. Okay.
Oh, from here.
A little higher. Can you
You'll be able to record the content. Create. Open. Okay. It seems some like issue here.
Well,
I think I sent my slides to you.
yep, I was going to say I will get them shared on my end. You'll just need to tell me when you'd like them to advance. Does that sound good?
Yeah, I think I can share. Let me try. Can you see my screen?
Yes, we're good now.
Okay, great. Thank you. My name is Yajing Liu. I'm a research scientist from Colorado State University, and I'm going to present our work on Hamming similarity and graph Laplacians for class partitioning and adversary image detection. So the first, let's talk about the background and what do we do in this paper. So we consider neural networks with ReLU activations. So for any given data input, so we consider a pre-trained neural network. So given a data point, so we only consider the hidden layers with ReLU activations. So we define bit vectors, which are vectors of like 1 or 0s, determined by the ReLU activation patterns. And we use the ReLU activation patterns, also called like a bit vector, to understand and interpret how the neural networks work. So first, we build a representational dissimilarity matrices based on the bit vectors at each hidden layer with ReLU activations to investigate the coherence of data within the embedding spaces of a deep neural network. And then we apply Fiedler partitioning method on the Laplacian matrix construct from the bit vector measures of similarity to classify images and detect adversary images. Finally, we also build a linear SVM classifier using the input of bit vectors in the last ReLU layer to detect adversary images. This let's give some like definitions we will use for the presentation. First, the bit vector. So I said we consider a pre-trained neural network with ReLU activation. So at each hidden layer with ReLU activation, so for a given data input, so we define a bit vector, which is a vector of 1 or 0s, and which has a length equal to the number of hidden nodes in that layer. And if the bit vector assigns 1 to nodes that activate the ReLU at the input point, 0 otherwise. We also use RDM, which is short for representational dissimilarity matrix. And that is, for building the RDM, so we have to consider like an input data set. So given an input data set, so at each hidden layer, we calculate its output. Then we build the RDM using the RDM is a square matrix. And each entry denoting the dissimilarity between the corresponding like output. And the dissimilarity metric can be, can be like a Hamming distance, like cosine distance, and all other distance. And the data set and the model we consider here, this let's talk about. The data set we use is ImageNet 1K data set, which has 1,000 classes. And in the training data set, each class has 1,300 images. In the validation data set, each class has 50 images. And in the test data set, each class has 100 images. We created adversary images mainly using based on the validation data set. And also we downloaded DamageNet, which was created by other researchers, also based on validation data set. So we created like another 3 classes of adversary images using the existing like method FGSM, PGD, and also CW. The pre-trained model we consider is ResNet 50. And it was introduced in 2015. The key point of this neural network is it uses skip connections to allow the neural network to skip some like layers. They can use the input of some earlier layer can be directly used as the output of some earlier layer can be used as the input of some like later layers. It can skip some layers to avoid the diminishing gradients or vanishing gradients problem. Let's talk about how we calculate the RDM. So I said we consider a pre-trained ResNet 50. Actually, it has like 50 layers, but it only has 17 layers has ReLU activations. So we only consider the bare products of that 17 ReLU layers. We use Hamming distance because for each hidden layer for any given data point, we define a bit vector of 1 of 0s. And for any 2 data points, we calculate the Hamming distance, just the number of entries, 1 or 0 different corresponding entries, different corresponding entries. The punchline of our method is that, because for the 17 layers, the first layer, remember, it has 800K nodes, and the total, the number of total nodes for the 17 layers is 6.3 million. But for each hidden layer, we only extract 1,000 significant features or significant bits using some we use select key best method from the second layer. And also we have training, we use training data to select the significant features. And then we use the selected significant features to get the cutted or shortened B vector for the test data. And then we calculate the RDM on the test data. And we investigate how the RDM evolves through the 17 random layers to explain how the neural network works layer by layer. And this is our simulation result. Here we have, because we have 1,000 classes for the entire data set, but we only look at two classes here. One is tench, one it's also one class of fish, and then another is snake. Because this is based on the we use a validation data set for test. So each class has 50 images. So when we build the RDM, we have the x-axis and the y-axis both have 100 entries, because the first 50 is from tench and the second is from center snake. And the bar values we can hear, because this is dissimilarity. So the smaller the value, that means they are more similar. From the first four figures, we can see the first four random layers, we can see all data points or images from the two classes exhibit similarity. That means the neural network try to find the similarity even among images from different classes. And then as the layer goes deeper, and the neural network starts to recognize the difference between the first class and the second class, the off-diagonal entries, so it's become more rarer. And also at some layers, for example, the 5 and 6, it starts to recognize more similarity in the second class. And as the layer goes deeper and deeper, the neural network try to find more dissimilarity between the two classes and more similarity in the same class. And at the last 3 layers, we can see the neural network can separate the two classes very well. Okay, and then we use algebraic method called feeder vector partitioning to do the classification or partitioning. So it's this method is we consider a graph. Okay, actually, as each data point we consider as a vertex of a graph, and we try to classify the nodes on the graph to subclasses. So we build a weighted adjacency matrix A, and then we can calculate the degree matrix and the Laplace matrix. The feeder vector is a V2 here, eigenvector corresponding to the second smallest eigenvalue of the Laplace matrix. And the Laplace matrix, how we build that, because adjacency matrix, we build that using the 1 minus the Hamming distance matrix, because it's the similarity. For the vector partitioning, so how that works, once we get the Laplace matrix and we get the eigenvector of the corresponding to the second smallest eigenvalue of the Laplace matrix, we only look at the sum of V2. For example, for that simulation I just showed, we have 100 images. So we have V2 should have 100 entries. And we look at the sum of the 100 image entries, and the index corresponding to V2 greater than 0, we classify as one class, and less than 0 to another class. And for those vertices that are corresponding to the vector equal to 0 can be classified into either class. Actually, we don't have any index corresponding to the eigenvector equal to 0. So I said we build the adjacency matrix using 1 minus the Hamming H matrix is a distance matrix. So it's constructed using the Hamming distance. And we do the same thing. We also utilize the feature selection to identify most crucial bits using a training data set. And then for test data set, we use the selected features to calculate the Hamming distance matrix, and then the adjacency matrix. And finally, we got the Laplace matrix. And then we apply feeder partition to Laplace matrix to construct it on the test data set. And here is our results. In the table here, we have a layer number. We have 17 layers, because we do every hidden layer. And the second row is the accuracy, the total accuracy for the classification of the two classes. And the third one is for Tunch. And the last one for the standard snake. And we can see the accuracy increase generally as the layer goes deeper, but it does decrease from layer 7 to 8. But if you look at the Tunch and the standard snake, you can see from layer 7 to 8, the neural network, try to classify standard snake, very well from 84 to 100. But for Tunch, it dropped a lot. So at some layer, neural network try to find the similarity for one class, but not for another one. But in general trend, it gets better and better. And in the last 3 layers, you can see the total accuracy is 100%. We also do the similar experiment on another 4 pairs of 2 classes. So we only plot the test accuracy on ReLU 1, 5, 10, 17, and we can see the increasing test accuracy, classification accuracy. Actually, the feeder partitioning algorithm can be used for multiple classification also. 2 to n can be 2, 4, 8. Just look at the same patterns of the eigenvectors corresponding to the first n, and then eigenvectors corresponding to the first n non-zero, the minimum non-zero eigenvalues. Yeah, we also do 2 superclass classification. 2 superclass means we consider Tunch and the goldfish both belonging to fish as fish, and also another 2 snake as snake. So we got also very good classification rate at the last 3 layers. We also do the adversarial detection, because adversarial, non-adversarial, also 2 class. We also got very good results. I'm not going to the detail, because finally we build because we find the normally people use the parameter layer or the latent layer embedding. It includes the most information, but the ReLU actually is before that. Actually, we find that the ReLU layer carries also a significant information. That's why we want to test whether we can just use the last ReLU layer as an input to detect adversarial. And because we already tried that, we build our SVM using directly on the latent layer or parameter layer embedding. So we got good results. Now we test on the last ReLU output as the input. So we still consider this data set, but we because the data is bigger, so we only choose 3 subsets of the data set. We have 3 data sets, and we use the last ReLU layer bit vector as input to build a SVM classifier, and also we use the parameter layer embeddings as input to build the SVM. We compare results. Now for the because the parameter layer has 248 dimensions. So when we do the feature selection with the ReLU output as input, so we do both 1000 and 2048. So we got a similar performance with the case for using the latent layer. But when we use even we use 1000 features, we can get comparable results. Okay. Finally, I want to conclude our work. So we demonstrated that the RDMs built based on the ReLU activation patterns can be used to interpret how the neural network works. And then we showcase that 1000 out of the, here is a typo, it should be 100K, order magnitude nodes carry enough information for representing the data. we applied the filtered partitioning on the Laplace matrix constructed from the bit vector measures of similarity to achieve like over 95% image classification accuracy. And finally, we built an SVM with input of bit vectors in the last layer that separates adversary images from non-adversary ones with more than 95% accuracy. I think that's all. Thank you.
Yes, thanks. Thank you. Let's thank the speaker. I think unfortunately, due to timing, we'll have to pass on questions, but feel free to the folks in the room here put anything in the chat or contact the author directly. And next up, we have Tegan Emerson.
We'll need her to stop sharing though. So we can- You have my slides. All right, well, thank you, everyone. I am presenting on behalf of excellent work done by a colleague of mine, Auden Myers, who's a postdoc at Pacific Northwest National Labs. I will be talking about our paper on top fusion, which is really looking and starting to explore how you can leverage sort of the universality and of topological features to perform multimodality fusion and what other things that might be useful for. So we have a large team here. And again, just to highlight, Auden is a postdoc. He is the second from the right as you're looking at it. And he did a lot of this work coming through it. So in terms of thinking about multimodality data fusion, there are sort of two umbrella ways that we think about this and how you could describe it. So feature fusion, this is where you will effectively, for each of your different modalities, when I'm saying modalities here, it means different formats of your data. So you could imagine having images and text, you could imagine having images and time series, but you have two different structures, or you could also have an array of sensors all collecting the same data. So you could think about wearable technology, and we'll have an application in that. But where you either extract features from each one of those separately, then you do some form of concatenation. You can also do this in a very sophisticated way, looking at different model architectures, multi-headed models, where you're essentially still concatenating those features in some modular way. And then you feed that into a collective decision model to make your overall final decision. The other approach would be model fusion. These are also often called early and late fusion. But model fusion is where you would essentially build modality-specific models or decision processes, and then you'd employ some form of a majority voting scheme, and what you want to do is make an informed decision. There's some things about these that are from, at least from a mathematical perspective, they don't always sit so well. You could imagine for different modalities, when you are going to just concatenate, you could have entirely different units for the different sections of your vector. You've mapped things to a very nonsensical, from a mathematical perspective, space. And so how can we also leverage that? A lot of what you see when you're doing these as well is it doesn't really explicitly capture the relationships across modalities. You can get it to some level implicitly, but you leave a lot to just sort of be inferred underneath. So what our approach was for this was topological data fusion, where here you take your different modalities, topological features. This is employing techniques from persistent homology. And those are essentially things that there's a different way that you extract them from each modality, but you're still effectively mapping and extracting the same core features from each of those modalities. And so you're going to go through, for each of your modalities, a filtration process. You're going to create a topological summary, which shown here is a persistence image, which is a vectorization of a persistence diagram, but there's many others as well. Then in our case, we're going to use these persistence images to create a multi-channel image. So create a tensor that we would feed in to some neural network-based decision model, so that we can then, as we convolve, for example, through those channels, we're able to compare features from one modality that's in the same feature space and look at the relationships directly between those features across the modalities. So in this work, we've sort of focused it on two things. There's two pieces here. One is, how should you actually extract topological features, and how do you strengthen their discriminatory power? So for example, images, when you think about the MNIST data set, a 1 is a 5 is a 7, is a 2? I think those are the right numbers there, right? They're all one connected component. They're all essentially, if you were to apply normal persistent homology through something called sublevel set filtration, you would see a single connected component, nothing too exciting. Whereas, and so you don't necessarily have the same discriminatory power that you would want to be able to harness in an ideal world. So we're going to present some work that Auden did looking at one way of boosting the discriminatory power for that modality and that data set specifically. The other piece is how can you actually leverage topology when you have incomplete data? So this is a problem that we face a lot in the spaces that we work in, where you could imagine if you have an array of sensors, one of those sensors goes out. What can you still do in that particular setting? And does this fact that you've mapped into a common feature space give you anything in your ability to better make inference in the presence of incompletely measured data? I think these videos are playing. So for the how do we strengthen, this is that example with the MNIST, the images, how do we actually strengthen the discriminatory power? This is a method that Auden developed that instead of doing sublevel set filtration, which is going to look at the different intensity levels in an image and go through them, and you look at connected components and neighbors and build a simplicial complex based off of that. He looked at how could we leverage zigzag persistence, which is a way of handling abstract simplicial complexes where you don't have a direct inclusion role. So where one always has to be included in the other, you can use unions and intersections as a way of connecting these when there is not a natural inclusion direction rule. And so here what he's doing is he's actually showing, so here you have the little loop. It looks like it has stalled out on me. It's probably because it's a very big GIF. So I will let them go, but this is just showing how you actually are creating these zigzag. I won't get lost in the details for this one here. I'm happy to follow up with anyone about it, but it does, we find, give us a much stronger discriminatory power in images, and it scales substantially better with the number of pixels, which is also important for a lot of the applications we're not showcasing in this work. So then the second piece of the problem that I mentioned is this notion of data completion and imputation for early fusion. So what we assume is that in your training scenario, you have this situation on the left where you have modalities you can extract, you have a complete data set that you're training on. And so you have the ability to extract your features and then feed them into your decision model. What we actually imagine in a lot of our operational scenarios is that you might have data modality 1 and you can extract the features there, but what happens if you're missing the other one? And so the first option would be to actually try to complete the missing data directly, try to approximate what you think that specific raw data should have looked like, and then extract features from that and feed it through. The other way is to try to complete the features directly. So can we actually infer what the features should look like in the based off of nearest neighbors and other methodologies? And so in what we think when we're talking about the original ways that people typically think about this for option 2, it's really hard to imagine what you would effectively be needing to do is figure out how do you define a relationship between one set of features and another set of features. That's made more complex by the fact that you also would have to include effectively unit conversions for things that maybe don't make sense, depending on how you're actually constructing those features. So our hypothesis is that that's actually a bit more difficult in the case where you're not having this existing universal space that you're leveraging. So what we did is we looked at 2 different data sets. This first one is called WSAT. It's the wearable stress affect detection data set. This ultimately has a downstream classification task attached to it, where you have different wearable technologies attached to somebody. They're collecting measurements that are supposed to be indicative of what their current stress level is. And then what you want to be able to predict is whether they're stressed, amused, or just they're in their baseline state. And so what we do here is for each of those time series, we've developed a filtration pipeline. I won't go into the details, but it leverages time-delayed embeddings to extract topological features from that data. And then what we want to know is what happens in this case. They have one that is attached to your chest and one that's attached to your wrist. What happens if one of those goes out? And so what we did is we created our actual baselines here. So the baselines are on the left. So this is if PIs here stands for persistence images. And so this is if you are just trying to build up this 3-class classifier based off of the topological features using only one modality. And so here, the first thing to notice is that if you look at wrist PIs, chest PIs, and then the third one that says wrist and chest, you are actually able to get a performance gain by performing the topological fusion. And then if you actually implement based off of one of the existing papers, we're able to outperform the other statistically based approaches that people use here. We are working on comparing these to more conventional state-of-the-art deep learning architectures as well. And so on the right is what happens if you actually now, okay, what we have are the wrist PIs. And what we're going to do is assume that for those test subjects, we don't have their chest measurements, but we're going to use a nearest neighbor-based imputation strategy to approximate what we think the persistence image should look like. And then we're going to feed that through and see what our overall accuracy is. And so here, what you really actually want to be comparing this to is that 84.3 that says wrist and chest PIs together. And so there is a performance degradation when you leave out one of the modalities, but when you compare it to the comparable degradation using a statistically based method, we actually are able to outperform in that setting. So we also looked at this for, again, a different data set. Here we have two separate or disparate modalities. So this is where we have images and audio. And so again, what we want to do is set up, we've developed the pipeline that is motivated in the paper. And so I won't go into that right now, but we do have, again, a classification task coming out of this. And then we see very similar results being carried through here as well. Instead of reading those to you. So yeah, this was really sort of our initial step and our initial foray into this space to try to understand, is there a benefit? There were lots of additional research questions that came out of this, but we did find that you could effectively leverage a topological feature space for these tasks in multimodality fusion. And while we do have, as is the case and one of the deterrents in a lot of settings for TDA, scalability does remain a challenge, but there are now approaches in software. And if we start to think more abstractly about the problem, we may be able to find ways to create more efficient filtrations like that of using zigzag persistence on images, which had not previously been done before. So with that, I think I will just try to get us a little bit ahead of schedule to switch because our last one of this session is also online. So I'm happy to take any questions.
So the parameters for most persistent filtrations tend to be connected to the geometry, sizes and scales. So if your different modalities operate in units that produce vastly different scales, is there a widening step in your process, or
how are we doing the normalization?
How are you dealing with the scale?
Yes, I think that's a great point. So for the applications that we considered here, I will need to double check Audin's implementation. But I believe what we did was we normalized the data on the front side so that we have everything on effectively the same scale for the persistence images so that you do have the same overall range. We're doing normalization in that space so that you have the same viable minimums and maximums for your birth and death scales. But I think it's an important question, and it is still one that's open around persistence images in general, is what is the right normalization? Should it happen on the data side? Should it happen after you've extracted persistence? And how does that affect your downstream performance?
Much wider than persistent images.
Yeah, oh yeah. Yes, absolutely.
Do you have any other questions?
So I don't know the zigzag technologies like that, but it sounds like you're basically trying to take some sort of shortcut filtration. And is that at all tailored to different data modalities that you consider, like strategies, things that you?
Yes, and so in ours, we actually do it from multiple directions as well. There's been, for images in particular, looking at how do you optimally use like persistent homology within the context of image classification when there's, it's something that so many state-of-the-art deep learning models do much better on, generally speaking. And so, yes, there is some degree of tailoring. What we are working on that is not in this paper, but we are working on a roadmap for how should you actually make the decisions about what filtration. So for example, when you have time series data as well, you always have the option, you could do a time delayed embedding. When is it reasonable that there's an underlying dynamical system so that assumption is viable? Or when do you do sub-level set on the lower star, rather on the time series directly and all those variations. And so it's not, there is some stuff under the rug there in terms of how are we actually making those choices.
Let us thank our speaker one more time. And Francesco, if you're online, do you want to share your slides and do a mic check?
Hello. Yes, let me share my slides.
Perfect. Your volume's coming through well.
And okay, can you guys see the slides and not the notes?
Yep, we see the slides. So
Okay, perfect.
Up to you to take it away.
Awesome. All right. So hi, everyone. My name is Francisco Acosta. I'm a PhD student at the BioShape Lab at UC Santa Barbara. And I'm going to talk about my project on quantifying extrinsic curvature in neural manifolds. This is work done with Sophia Sanborn, Kandao Duk, Manu Madhav, and my PI, Nina Miolan. So I'll start by introducing the idea of neural representations. So the brain needs to represent information about the world for decision-making, problem-solving, planning for the future. And in order to do so, it needs to have some kind of coding scheme or a neural code to store information in the patterns of activity of neurons. So the kind of neural code that we're going to consider here is called rate coding. So if you look at an individual neuron and you stick an electrode near that neuron, you can record its electrical activity or its voltage through time. And you will see these events called action potentials where the voltage spikes on a time scale of about 1 millisecond. These are called action potentials or spikes. And you can record the voltage from multiple neurons at the same time. Here we have 3 neurons, for example, and we keep track of these spikes. So these are the individual blue lines. The idea of rate coding is that information is encoded in the rate at which these neurons are firing or spiking. And we're going to compute the rates by time binning our spiking data into time bins of duration delta t. So we do that for the entire data set. And we can compute the rate at which neuron I is firing at time t as the number of spikes of that neuron at time t divided by the duration of the time bin. And so this gives us a number that is in units of spikes per second. And if we have a population or a circuit of n neurons, we can organize it into a vector that is in n-dimensional space, where each coordinate is the activity of a single neuron. So this is how we build this space that's called the neural state space. So this is a space where each coordinate axis corresponds to the activity of a given neuron. And here, every orange point in this neural state space represents a particular environmental state. So at a time t0, we have a particular neural response, which corresponds to a point in this vector space. And as we vary time, as we vary the incoming stimulus, and the animal explores all the environmental states, we get a collection of points in this neural state space. And this collection of points we're going to call the neural representation for this task. And the neural manifold hypothesis is the idea that in many cases, the dynamics of the circuit is constrained to a much lower dimensional manifold within the high dimensional neural state space. So here, for example, we're recording from arbitrarily large population of n neurons, but we're depicting the neural representation as being a one-dimensional manifold, a ring in this space. So this is the neural representation, which I'm going to call neural manifold in general. And so we have these abstract objects and these manifolds in neural state space, and these neural manifolds represent important information about the world that our brains use to solve problems. We want to study the mathematical structure of these neural manifolds. So one set of tools that's been employed successfully is topological data analysis, like persistent homology, to study the number of holes in point cloud data recorded from populations of neurons. So this has been applied, for example, to a head direction circuit, which is a population of neurons that stores information about 2D orientation in space. So it encodes the angle at which your head is pointing in relative to some reference direction. And people found the underlying one-dimensional ring in this high-dimensional neural state space using persistent homology. Similarly, for grid cells, which are a type of neuron that are involved in navigation and keeping representation of physical space. By the way, if you're a mathematician or a physicist, you will find grid cells really fascinating. And their theory predicts that their collective activity should lie on a torus. And recently, people used TDA to uncover the underlying two-torus structure in the neural state space for the grid cell circuit. So these are all great. And what we want to ask here is, can we have a slightly more detailed geometric description of these manifolds? And we're going to work within the framework of Riemannian geometry. So Riemannian manifold Z, we're going to call it Z, is a manifold where at every point there's a tangent space, and we have a Riemannian metric, which is a function that assigns to every point an inner product. So it takes two vectors in these tangent spaces, returns a real number. Roughly speaking, when you have a metric, distances and areas involve taking integrals of the metric, and things like curvature involve taking derivatives of the metric. And once we have a manifold with this metric, that's called a Riemannian manifold. For curvature, which is the geometric feature that we're really interested in here, there's two main types of curvature. So there's intrinsic curvature. So you can compute that, making no reference to any kind of higher dimensional embedding space. So here we have things like the Christoffel symbols and the Riemann curvature tensor, which you can then contract to get Ricci curvature tensor and Ricci scalar. So these are all notions of intrinsic curvature, which is the curvature that is behind, for example, in general relativity, that explains the curvature of space-time, explaining gravitation. We're going to be interested in extrinsic curvature, which does make a reference to a higher dimensional embedding space. This is probably the more familiar notion of curvature. And we're interested in how this neural manifold curves within the embedding space, within the neural state space. So how do we go about that? What can we give a metric to this neural manifold? And the way we're going to do that is we're going to use a tool called the pullback metric. So we're going to model the neural data that we have here as a point cloud manifold due to the manifold hypothesis in the neural state space X with underlying manifold structure M. So M is a submanifold within X. And we're going to say that the points in this manifold M are generated by a function F that is parametrized by these latent variables Z. And we're going to add Gaussian noise to get the points in the neural state space X. And so now we have a generative model, this function that takes us from some latent space Z to the neural state space X, where the neural manifold now is the image of Z under this function F. So if we have this function from Z to X, the differential of this function, which is a generalization of the first derivative or the Jacobian, is this map that takes you from the tangent space on of a point in Z to the corresponding tangent space in X. And so if this function is injective, then the function F is called an immersion. And if X is a Riemannian manifold, and this function that takes you to X is an immersion, then we can define a Riemannian metric on Z via the pullback. So what you're doing is you're pulling back the geometric structure on X via this function F onto the manifold Z here. So essentially you're computing inner products in Z by first using the differential map to send them to X, compute the inner product there using the metric for X, and then identify that as the inner product of the two vectors in the tangent space of Z. So if we have this function from Z to X and a metric on X, we can define a metric on Z. And if we have a metric, we have everything we need about the geometry. And so we can compute a notion of extrinsic curvature. The particular notion that we're interested in is called mean curvature. And so the mean curvature is given by taking the trace of the second derivative of this function F, the embedding here. And if you just write that out, so the gammas here are the Christoffel symbols, the gammas with the twiddle on top are the Christoffel symbols for the neural state space. So X, and we're using Einstein notation here, so all the repeated indices are summed over. And because the embedding space X is Euclidean, the Christoffel symbols, so the gammas with the twiddles are actually 0, so this expression simplifies a little bit. So this is how you would compute once you have this pullback metric, and using that function, how you would compute something like the curvature on this latent manifold that we're using here. Okay, so moving on, how do we actually learn the geometry? How do we employ deep learning for this use case? So this is the kind of architecture that we are proposing. What we have here is that we have a collection of points. We have our neural representation in neural state space. We're going to pass that through an encoder. So we're using a variational autoencoder here. We're going to pass it through an encoder to get points in a latent space. This is going to be our manifold Z. And our decoder, if it's trained successfully, is going to approximate a function from our latent space Z to the neural state space X. So it's going to approximate this function F that we were after earlier in order to give geometric structure to our template manifold Z here, which we're going to identify with the neural manifold. So the basic recipe for our technique here is you find the topology of a neural manifold using TDA. Once you have that, you set that topology to be the topology of your latent space in the VAE. So we implement that for hyperspheres, so spheres of any dimension, as well as products of hyperspheres, so things like tori, as well as Euclidean space. So you run TDA, that gives you what the topology of your latent space should be, and then you set that as the latent space of your VAE. So we have that here. Then the next step is to learn the deformation. So we train our VAE, and the decoder is going to approximate this function that takes us from the latent manifold to the neural state space. And once we have that, we're going to extract the geometry from this learned function. So we're going to pull back the assumed Euclidean metric in the neural state space. That's going to give a metric structure to the manifold Z. And then we can compute the mean curvature to understand how it curves within the neural state space. Now, there's a couple of problems that we tackled, things like VAE non-identifiability, which is the idea that if you have a VAE with a certain decoder F and latent variables Z, there are certain transformations that you can apply to the latent space or reparametrizations of the latent space that lead to different decoders, but the VAE being equally optimal. And in this case, interpreting the geometry of the latent space is unwise, and because the geometry becomes distorted by these reparametrizations. So we tackled that by fixing a parametrization using a supervised loss term to ground the latent parametrization. So this ensures that we can extract meaningful information about the geometry of the latent space. And so we ran this on synthetic data. So we did it for rings or one-dimensional circles. On the left here, we have the sort of the true synthetic data set, and then we have the learned data set by our VAE. And on the right-hand side, we're plotting the learned curvature as a function of the angle. And we show that we can do pretty well here. We also ran similar experiments on spherical data sets. So we're able to reconstruct the spherical data, and then we're also able to compute the mean curvature at every point on the sphere. And similarly, we did it for tori. And now we show the applicability for real neural data using hippocampal data. So these are neurons that are also involved in navigation tasks. So here we have a rat that is running around a circular track. And what we're able to do is record from these neurons, these place cells. And in the top panel, we have sort of the recorded ground truth neural activity for this population of place cells. We're able to reconstruct that well and learn a good parameterization for the latent manifold. So let me emphasize that this is 12 neurons at a time. So this is a 12-dimensional space, but we're able to visualize the curvature of this neural manifold embedded in 12 dimensions. So this gives us an idea of the geometry of the manifold, even though we can't directly visualize the 12-dimensional space. We did some error estimation by varying the input noise to the neural manifold, varying the embedding dimension, and we still need to do some more benchmarking and extensive error estimation, especially because real neural data can be quite messy. Running out of time here, but we'll run to the conclusion that we leveraged Riemannian geometry and these topologically aware deep learning models to quantify the extrinsic curvature of neural manifolds in the ambient neural state space. And this method allows for visualization of the geometric structure of manifolds in high-dimensional spaces. And this may open the door to investigate the geometric correlates of neural circuit function. So with that, thank you for your attention. And yeah, I'll take any questions if there are any.
Let's everyone thank the speaker. We are at time, but if there's a quick question in the room, otherwise Francesco put up his contact info here. You want to come up and
Hello, can you hear me?
Hi, yes.
I mean, other than the results showing on the primitive shapes, do you have some results on real shapes or some more interesting structures, complicated ones?
Yeah, that's a great question. So for the, oh, sorry about that. So I briefly talked about hippocampal data. So this is data of recording from rats running around a circular track. Let me just play that here. So these rats were running around the circular track, and we were recording from neurons that tile physical space. So basically we have neurons that fire at individual locations along the circle. And when you run topological data analysis on these kinds of neural circuits, you find underlying a circular structure. So you have a ring structure in this high dimensional space. And so we applied it to this kind of neural manifold, and we were able to visualize the curvature within this space. There are other kinds of neural manifolds. I briefly mentioned grid cells that have this underlying toroidal structure. That's something that we want to apply it to as well. But thus far, we've only implemented this for sort of low dimensional hyperspheres and then tori. So it is an interesting question of how can we combine sort of these primitives in order to investigate maybe more complicated neural manifolds. That's still a very interesting question.
thank you so much, Francesco, and let's thank all of our speakers from this morning's session again. So we're going to go on a bit of a lunch break now.
It's lunch until 1:30, where we will have our second keynote, so to kick off our afternoon session. And then we will also be announcing at that point the location of the sort of unhosted social hour for the community as well. That will be within walking distance at the end of today. So please come back and we will see you this afternoon. Enjoy your lunch.
Yes, thank you, everyone. And we also have 5 more amazing spotlight talks this
Yes.
afternoon.
You want to just close out of the Zoom for lunch?